Good afternoon, everyone. How's everybody doing? Good, I hope. My name is Michael Fischer. I am a Principal Specialist Solutions Architect at AWS. I've been at AWS now for a little over 4 years. My current role is Principal Specialist Solutions Architect for EC2 Graviton. Before that, I was also a specialist in AWS Container Services, so ECS, EKS, Fargate, ECR, and all the rest of the related container services at AWS. I've been working on EC2 Graviton for a little over a year now at this point. And I'm here today. The original title of this talk was Getting Ready for the Multi-Architectural Universe. But really what this is about is getting ready for ARM64. And the subtitle is Faster, Cheaper, More Sustainable Computing in the Cloud. And what I hope to do is convince you all today that, in fact, all of these three things are true, and why it's worth considering ARM64 and potentially even migrating to it if you haven't already. On my agenda today, went a little bit too far, let's try that again, is number one, it's not just an x86 world anymore. As a matter of fact, I hope to convince you that that multiple architectures, including x86, ARM, and others, are actually more of a return to normalcy than the status quo of the last 15, 20 years or so. Why you should consider migrating to ARM64? I'll give you three very good reasons why. Number three is who's doing it. As a matter of fact, many of your peers in the industry have begun migrating already. Big names that I'll talk about who are blazing the trail and have demonstrated that migrating to ARM64 is in fact a project that you can accomplish, that you can have good results from. And then how to adopt multi-arch yourself and be successful at it. I'm going to give some high-level advice on how to do that. And after the talk, if you'd like to talk about more specifics on how to accomplish multi-architecture, I'm more than happy to make myself available and chat with you over lunch on how to do that. So, part one, it's not just an x86 world anymore. So how many of you own a mobile phone? How many of you know what kind of processor is in your mobile phone? It is quite likely to be ARM64 based. I know, for example, anyone who's using an iPhone, for example, is definitely using it. Android may vary, but I know for sure that many Android phones are also ARM64 based. But it's not just about portable devices anymore. Although a lot of the engineering around hardware has gone into mobile devices, because when we started going from dumb phones to smartphones, we needed basically a general purpose computer, and that's what this is. But we needed it to be fast, we needed it to be light, we needed it to be inexpensive, and we needed it also to be very power efficient, right? And so that's what drove modern CPU designers to build ARM and other similar low power CPU architectures. But what happened is it started to evolve. People started to see that there was a life beyond simply mobile devices for these modern processors. So how many of you know what that is? What is it called? That's right, Raspberry Pi. How many of you have gotten one lately? They're at least in the US, they're difficult to get right now, but they're extremely popular. I have colleagues, for example, developer advocates at AWS who've built entire Kubernetes clusters out of Raspberry Pis. Raspberry Pis are amazing. They're about this big, about the size of a pack of cigarettes, and they're very low power, but also real bona fide computers, right? They can run Linux, they can run Ubuntu or Raspberry Pi Linux, 64-bit, gigabytes of RAM, flash storage, high-speed networking, Wi-Fi, HDMI output, USB in. These things are amazing. And then they also have this cool GPIO header on them so that you can attach all sorts of neat devices to it. So Raspberry Pi, first available general purpose computer based on ARM64. My Mac, which is in my backpack over here, So Apple released the MacBook Pro based on the M1 processor a couple of years ago. Does anybody have one? Yeah, I have one too. I love it. What's the greatest thing about it? Silent. Doesn't run hot. Isn't it amazing? And you can load the CPU and it won't even get your lap warm anymore. And now ARM64 is available in the cloud. So a few years ago, AWS actually introduced the original A1 EC2 instance family. Has anybody heard of A1? So A1 was a bit of an experiment. It was AWS's first experiment in using ARM64 architecture in the cloud. And so we had customers who were actually migrating their workloads to it with some success, learning lessons from it, talking to us about what they learned, and then we've built on that with AWS Graviton 2 and Graviton 3 instance families. This talk is not about AWS specifically. It does have our logo on it, but I did want to say that AWS has a lot of experience in it, and other cloud providers have introduced ARM processors as well, which I'll talk about later. But the fact of the matter is that the x86's popularity, basically dominating the server market, is actually a blip in time. So those of us who've been around, I've been in the industry now for over 25 years. My first experience with a Unix server was actually not on x86 at all. It was on a different kind of processor called a Sun Spark. Has anybody heard of Sun Microsystems? They were bought by Oracle about 10 years ago, but they were one of the pioneers in internet servers. So folks like me who grew up in the late 90s, or who grew up in the 90s, who first got access to the World Wide Web at that point in time, almost every major internet company on the internet was serving via Sun Workstation or Sun servers. These were based on a RISC processor known as Spark, powered major websites like eBay. I believe Netscape itself was powered via SunSpark. Many of the banks, early banks who were on the web, were based on SunSpark as well. But I mean, the legacy goes all the way back to mainframes. We also had desktop computing. You may have used a Macintosh early on before Mac OS 10, so maybe Mac OS 9 or even earlier. Mac was based on PowerPC for a long time, and also Motorola 68K. And then we also had workstations in the 1990s, including, I mentioned Spark earlier, but we also had DEC Alpha, which I believe one of the speakers yesterday, the one who was an former Amazonian as well, he also talked about how Amazon used DEC Alpha for a while. PowerPC, MIPS, Titanium, those were all names that were introduced in the 1990s. And so there was a healthy competition for a long time in the server world. Even Windows NT, which is the ancestor of Windows 7, Windows 10, Windows 11, ran on 4 different CPU architectures for a while. You could actually run Windows NT on DEC Alpha. You could run it on MIPS. And you can run it on PowerPC and x86. So as a matter of fact, nobody even really considered running internet servers on x86 in the 1990s because there was no 64-bit version of x86. So prior to that time, x86 was only 32-bit, so it could only access 2 gigabytes of memory. That was the maximum. I mean, technically 32 bits is 4 gigabytes, but for various reasons it was limited to 2. But then a company called AMD, how many of you have heard of AMD? Introduced a set of extensions to x86 that they called AMD 64. You may, if you log into a Linux box today and you type like uname-m, you may see AMD 64 instead of x86 64. There's a reason for that, and that's because AMD invented the 64-bit extensions. Intel, on the other hand, saw Titanium as its future. That didn't actually happen. And so what happened is Intel actually adopted the AMD 64 extensions. That's how we ended up with a 64-bit x86 processor family. And that's finally when Linux and other operating systems like FreeBSD really began to take off, because then with the 2 gigabyte memory barrier broken, one could run very powerful servers on x86, and that's how it actually began. So the domination of x86 for serving the internet is actually kind of a relatively short-lived phenomenon. And now what we're seeing is, since the mobile revolution has led to the evolution of low power, high performance, sustainable processing, we're now starting to see cracks in the foundation of x86 dominance. And there's very good reasons for that, which I'll talk about. So why should you all here even bother considering a new architecture? Given that the work that we'll talk about that needs to be done. Well, there's 3 reasons. Number 1, performance. And I'll get into all these in detail. Number 2, cost. And number 3, sustainability. How many of you care about at least one of these things? Great. And that's why you're here, I hope. All right, so let's talk about performance. ARM64 instances are up to 30% faster on x86. And really, there's a reason for this. It is partly because of a more advanced manufacturing process. So x86 processors, how many of you are familiar with what's called manufacturing process? So I'll just speak about this really quickly. How many of you have heard of Moore's Law? Okay, so Moore's Law says what? Moore's Law says you can double the transistor density on a CPU, on a processor, I think it's every 7 years or so. This actually is a consequence of the shrinking every year of the circuitry on a CPU. The smaller the circuitry on a CPU, the less heat it generates, because fat wires basically generate more friction in the transmission process than thin wires do. And so as a consequence, the smaller the wires are, the less energy it takes to basically operate a processor. And so companies like TSMC, for example, have been very inventive in basically making it possible to design smaller and smaller and finer circuitry inside the CPUs. So that's called the manufacturing process. x86 processors, I think, are hovering around 9 nanometers. Basically, that's the thickness of the wire. A nanometer is 10 to the negative 9 meters. Currently, ARM64, on the other hand, are built to 7 and 5 nanometer processes. 3 nanometers is on the way. As a consequence, not only do they run with less energy, but they're also able to run more efficiently and add additional circuitry that make CPUs faster, like pipelining, better speculative execution, and so forth. They're also a simpler design. x86 processors have a lot of historical baggage in them. As a matter of fact, when you power up an x86 processor, it still runs in a mode that is compatible with a PC from 1985. It runs in 16-bit mode, 8086 emulation. You can run MS-DOS on it if you want to, or CP/M. Probably don't want to, but there's a ton of circuitry in there that is built to for backward compatibility that's not needed on ARM64. Another major difference between ARM64 and x86 processors is that most, if not all, ARM64 processors built for the server have every core presented to the operating system is a physical core. This is in contrast to SMT or hyperthreading. How many of you are familiar with hyperthreading? So just really quickly, hyperthreading is a phenomenon by which a physical core, like a physical CPU, can present itself as 2 to the operating system. They're not both real. Only one core is real, but through some clever design, the processor presents one core as 2, and therefore the operating system can actually run 2 separate threads on these 2 virtual cores at once. However, since they're not both real cores, you don't get 2x the performance out of it. You get 1.5x performance out of it. If you've ever driven an x86 multi-CPU server to full load, you'll see what happens is, if you look at it in a normalized fashion, you'll see that it gets about 1 full CPU, then about 1.5 full CPU, but you can never really break that 70% utilization barrier. Your process latency or your application latency will skyrocket after that. With ARM64, on the other hand, every core, every CPU presented to the operating system presents as a full core. This actually allows you to load your servers much more than you would otherwise. And this is great for CPU-bound workloads. For example, on EC2, you can actually get an ARM64 instance with up to 64 CPUs. And those are real CPUs. So you can actually run a multi-threaded application using all 64 CPUs and get 64 full CPUs of performance out of it. And then the other is a full mesh architecture. In the ARM64, how many of you have heard of NUMA, something called NUMA? Okay, so in a NUMA architecture, the latency of memory depends on which CPU is running a particular task. So if you have an application on CPU 0 and an application running on CPU 1, their ability to access memory is not necessarily the same on an x86 system. So it may take slightly longer, just a few nanoseconds longer, to fetch some data out of memory, depending on where in memory it is, on CPU 0 versus CPU 1. With ARM64, on the other hand, all of the ARM64 instances that are available in the cloud are full mesh architectures. Every CPU has the same access to memory as every other CPU, and I/O as well. This means you get much better tail latency in your applications, much more consistent performance overall, and in general, much lower memory latency on average. All right, next, cost. In general, from all the major cloud providers, ARM64 servers are less expensive than x86 servers. Why is that? Well, it's because, number one, is that the cloud providers are participating in design separated from manufacturing. Cloud providers are able to take designs from ARM, Advanced RISC machines, which is basically the designer of the processor. They're based in Cambridge, UK. And they're actually, ARM doesn't tell you exactly how physically to build your processor. They either give you a specification in terms of instructions, if you're a CPU designer, or they give you some what are called Verilog files. These are basically files used by CPU manufacturers in order to design. It's basically the placement of all the circuitry and everything like that. But it's really up to the manufacturer to figure out exactly how they want to produce these CPUs. And so cloud providers are able to take that intellectual property from ARM and design a CPU that is custom built for the specific application that they want to use. So when I have my phone here, my phone's manufacturer is actually able to take the core design, customize it for the low power form factor that they want to use, and then produce their mobile devices with it. Same goes for server manufacturers. Broadcom, who built the CPU for Raspberry Pi, was able to build a custom CPU for Raspberry Pi. Same thing goes for the cloud providers. They're able to actually take what they want, discard what they don't need, that's not going to provide value for the customer, and they're able to produce these at cloud economies of scale, and therefore produce them at very low cost. We talked about the relative simplicity of ARM64 processors. They don't have the legacy baggage, and so there's far less circuitry in terms of transistor count needed to provide the same functionality. And then the other is, of course, energy utilization, which I'll talk a little bit about more because it also bleeds over in sustainability. Because ARM64 processors require less energy to run because of their advanced process, cloud providers are actually able to pass the value, the savings of the less energy consumed onto the customer like yourself. All right, let's talk a little bit about sustainability next. So because of the engineering design that I talked about earlier, ARM64 servers use less energy than x86, up to 60% greater performance per watt. That's astounding. That is literally a world-changing phenomenon. If you could basically, how many of you own a car, right? Let's say that you went to a gas station who promised you that you could drive 60% further with their gasoline than with the gas station across the street's gasoline. Would you buy it? Absolutely, like no question, right? That's basically the same thing as the value delivered by switching to ARM64. But what it also means is not just sustainability in terms of energy consumption, but it has second order effects as well. That 60% greater performance per watt means that cloud providers can greatly improve the overall density of their physical server installation inside the data centers they operate. And by doing so, if you're able to actually condense racks together because you're able to build more dense racks because they use less energy, it means that you need less real estate. In other words, the building doesn't have to be as large to fit the same amount of capacity. It also means that you don't need to air condition as much space either. And air conditioning is a very expensive, very energy. It's a very energy inefficient, very energy consuming process. And every single cloud provider is committed to reducing its climate impact significantly. AWS, for example, has committed to a 100% renewable energy target by 2025, and going net zero in terms of carbon by 2040. Microsoft has been carbon neutral across the world since 2012 and commits to being carbon negative by 2030. And Google has been carbon neutral since 2007 and has a target of being carbon free by 2030. Just a quick show of hands. How many of you work for a company that has sustainability goals, published sustainability goals? Okay. Still a minority here in this room, but I expect in the fullness of time, most companies around the world will have sustainability goals, probably by the end of the decade if they don't already. So, if you're going to adopt ARM64, you can breathe easy. You're not the only one. In terms of industries that have already adopted it, they're all over, right? Finance, Ascend Money, for example, has adopted EC2 Graviton. Social media, Snap. How many of you use Snapchat? Anybody? They've adopted ARM64. Gaming, Epic Games. Anybody play anything with Epic Games? Fortnite, for example, also runs on ARM64. Chip making, electronic design automation. Cadence is a big chip maker, is using ARM64 for their EDA. Media, Discovery Media is running on ARM64 for video transcoding. Sports, Formula One. Anybody racing fan? Formula One now uses ARM64 for doing their computational fluid dynamics. Health tech, HaloDoc is using ARM64. And e-commerce, Mercado Libre, which is basically the buyer-seller platform of almost the entirety of South America, is using it. Formula One, for example, was able to reduce their computational fluid dynamics by 30%. Honeycomb.io, I believe Charity is here, they actually have completely migrated to ARM64 entirely. They've saved 40% on their ingest costs and have reduced their instance count by 30%. 30%! Imagine being able to discount your virtual compute by 30% by switching. That's huge, huge. Snap, as I mentioned earlier, has migrated their messaging core service and their memory cache service with a lot more to come. So, although I work for EC2, again, this is not an Amazon talk, every cloud provider has begun introducing ARM64 instances. So EC2 Graviton, I've talked about. Oracle Cloud Infrastructure has Ampere A1 instances, which you can use. Microsoft Azure, their DPS v5 and EPS v5 They're in preview today. Google Cloud, their Tau T2A instances also in preview today, which you can adopt if you so choose. So, you've made the decision that you're going to migrate to ARM64. How do you get ready? How do you accomplish this migration successfully? Well, basically, there are 5 major stages to it. Number 1, identify and prioritize your workloads. So, those of you who want to adopt ARM64 may find it easier or more difficult, sort of depending on what your software is. So how many of you are using containers today? Kubernetes or ECS or one of the other cloud providers' container services. How many of you are using Kubernetes again? Anybody using ECS, Amazon ECS? Docker Swarm? Others around the room? Okay. So containers are actually one of the easiest ways by far to adopt multi-architecture. How many of you know that the container image format, for example, if you do Docker build, actually supports multi-arch already? So you can actually, for very common base images like Nginx, for example, any of the Java base images, Node.js, all of those have multi-architecture base images available today. If your software is pure scripting language, pure Python, pure Ruby, pure JavaScript, pure PHP, all of those can run on ARM64 because the runtimes for those, the scripting language hosts, have already been ported. They're already been, in the case of all of those, Ruby 3, for example, has been especially optimized based on input from ARM's software team to actually run faster than Ruby 2, for example. The other is, how many of you are running Java workloads? Anybody running Java? So if you're running Java, if they're pure Java jars, if they're not using JNI, for example, they too, you could even compile a Java jar on x86 and run it on ARM64 as is, just by switching the Java runtime from x86 to ARM64. So the first step is basically figure out, what can I run on ARM64? And the answer is probably the majority of many workloads already do. And so the one exception would be if you're running code that was compiled like yourself in C or C++, you may have to recompile it in ARM64. But all the major compilers, GCC, LLVM, CLang, they all work. They all have the ability to either natively compile or cross-compile to ARM64. And the compilers are being improved all the time. So one of the best ways to make sure that you get the best performance on ARM64 is to make sure that your compiler is updated to a recent version if you can. It's always best, if you can, to compile on hardware that matches the architecture. However, it is also possible to cross-compile in 2 ways. You can cross-compile in Docker Desktop, often by using Docker BuildX. That supports software emulation using QEMU. Or if you're building software in C or C++, you can often do something called cross-compilation by specifying what kind of target you want as an argument to the compiler command line. If you're using Go or Rust, any Go folks or Rustaceans here? So if you're using Go, you can simply set the Go OS and Go Arch environment variables. You can set them to a foreign architecture like ARM64 and Linux, and it will actually produce that, right, no matter what you're on. You could be on a Windows x86 instance and it would work. Same thing with Rust. I believe it's cargo build -- target. You can also specify a foreign target as well, and it will compile for the target architecture. So you've identified and prioritized the workloads that can run. Another thing to look at is, of course, what is going to be your greatest win in terms of cost by migrating as well. Identify, some of the lowest hanging fruit are going to be serverless functions, for example. A lot of folks, anybody running AWS Lambda or similar serverless? So AWS Lambda, for example, allows you to simply switch from x86 to ARM64. You may not even need to change your zip file. If it's just 100% pure Java or scripting language, you can simply change it in the dropdown or change your Terraform template or your CloudFormation template, and you can actually run your Lambda function on ARM64, save 20% by just making that little switch. Also take a look at CPU-heavy workloads. What are the things that use the most CPU? Oftentimes, you can migrate those to an ARM64 instance family and shrink the number of instances, like some of our customers have. So take a look, see, look at your bill, let your bill and your software kind of dictate in what order you choose to migrate. Once you've done that, you'll need to begin updating your pipelines, and I'll talk about that a little bit. When you migrate to ARM64, you'll need to evolve your pipeline a little bit to accommodate multiple architecture builds and deployments. As part of those pipelines, of course, you'll want to test. Then, once your tests have passed, you'll begin deploying it to your new ARM64-based architecture infrastructure. And then, after successfully deploying into production, you can begin to retire the older x86 infrastructure that you had before, and then begin enjoying the savings and the sustainability and the performance of ARM64. So, this is an example pipeline of what a multi-architecture build looks like. It looks like any other typical DevOps pipeline for doing build, test, release. On the left side, we have the pipeline is triggered by a push to a code repository in a given branch. And once the code has been pushed, then the build and test process begins. So one of the differences between this and your typical pipeline is that we actually have here here we go, okay. We actually have a split pipeline. The upper half of the pipeline runs the build and test process on x86 as you've been doing before. The bottom half of the pipeline does the same thing in parallel, except on an ARM64 build target. And so there are many ways in which you can gain access to, what if you don't actually have ARM64 build infrastructure already? Well, there are many ways to get it. So Circle CI, for example, provides ARM64 build hosts. If you're using AWS, Code Build supports Graviton-based build hosts. And I have a forthcoming blog talking about how you can actually attach Graviton-based instances to your GitLab and GitHub projects by using self-hosted runners that are managed by Kubernetes along with Carpenter. So the key, one of the key things here, which I'll talk about, let me go on a little bit. Once you've built and pushed and tested on both x86 and ARM64, if you're using containers, you can actually build and push a multi-architecture manifest. So what you do in each of these stages is you push your Docker image for your specific architecture to your image repo. So that could be ECR, could be Docker Hub, could be Artifactory, or whatever registry you happen to be using. Once you've pushed the architecture-specific images, then you stitch them together using either an x86 or ARM64 build host by using a Docker manifest command. That will basically get the image saws for the architecture-specific container images and create a multi-arch architecture-neutral container image manifest, then push that back into the registry. Then once you're done, you can deploy. So as I mentioned before, one of the great things about a multi-architecture manifest is that it means you can actually deploy your application either on x86 or on ARM64, however you see fit. And this model is, it's really pipeline provider neutral. This could work on AWS Code Pipeline. It could work with GitHub or GitLab, Jenkins. It doesn't really matter. What matters basically is the process. So I want to actually double click a little bit on testing. So test automation is important, and it's more and more important every day. How many of you actually have automated tests for all of your software today? And is it part of your overall build pipelines? Yeah. So I encourage you to, if you haven't already, continue to invest in your test automation. I hear ChatGPT is making it easier to do that. But continue to invest in your test automation, and you want to test each architecture on every build. That's really important. So deployment and promotion. The process is really straightforward. You start with ARM64 lower environments like test and other integration environments, dev environments, and you maintain those ARM64 lower environments since you have an ARM64 production environment until you're fully completed the migration. And then use canary deployments or blue-green deployments for the initial production rollout to minimize your risk. So one thing I did want to caution folks about is that it is tempting to cut corners in the testing process. For example, one might do a build and push for x86 and ARM64, but only actually do the testing on ARM64 or do the testing on x86 and make a conclusion that the passing of tests on one architecture implies the passing of tests for all the other architectures that you may be building for. The thing is, it's not actually recommended because although we don't expect in the usual case any sort of bugs that are architecture specific, it can happen in certain very specific corner cases, especially if you're dealing with IEEE floating point math. For example, I have a customer who basically uses IEEE tons and tons and tons of IEEE floating point math for the purpose of making weather forecasts. And it's not that the forecast came out any different, but what was happening is that their tests, which basically tested known data sets with known results, had very slight differences in the result output on ARM64, and as a consequence, we had to work with them to figure out what the source of those errors were. It's extremely uncommon. However, and even Kubernetes, for example, doesn't yet have a full ARM64 test suite, and yet people run Kubernetes on ARM64 everywhere. But as a best practice, we do recommend testing on both architectures, if nothing else, because one of the main differences you will see on ARM64 potentially is differences in what the throughput and capacity testing looks like. Does anybody currently do capacity stress testing as part of their automated test pipelines? It's not common. It is a good practice, but it's not very common to have regression tests in terms of load test capacity. So we do recommend that. Usually ARM will come out ahead. However, I think it's important to test on both. I'm sure many of you know that software changes actually can impact production often just as much, or if not more, than architectural changes can. So just a bit of high-level advice about migrating to ARM64. I'm happy to answer for you all specific questions about how to migrate, how to prioritize for migration, the benefits of switching, capacity concerns, or anything else you'd like to ask about migrating to ARM64. Thank you so much.